Hello everyone, welcome to my virtual talk. My name is Florin and this is joint work with Maria and Willy, and we are from the University of Sydney. The talk is about three interesting performance anomalies that we uncovered on SSDs. These performance anomalies present themselves as read throughput variability. Consider this plot. It shows read throughput over time. On the x-axis, we have time, specifically a 10-hour window. On the y-axis, we have read throughput. These are HDFS reads. A single 256 megabyte HDFS block is read repeatedly over the entire interval. Each dot in the figure is one such block read. Normally, knowing the maximum performance of our SSDs, we would expect to constantly get about 430 megabytes per second. This maximum performance is represented by the horizontal orange line in the figure. Unfortunately, in reality, what we get is a great amount of variability. Also, we often do not obtain maximum performance. In this talk, I will be describing three new types of variability, and I am briefly introducing them here by encircling them in red. There's the big performance drop in the middle, the large variability on the left, and the periodic drops on the right. For each of these problems, we will be looking at symptoms, and then we analyze whether strategies available at the user level can mitigate the problem. So where does the variability come from? On the left, you can see a high-level depiction of the internals of an SSD. In the middle, you have the FTL, the flash translation layer, a critical piece of software and hardware that manages SSD operations. Its task has become increasingly complex over time, as it is managing many internal operations like garbage collection, wear leveling, error correction, page allocation, read disturbance management, and so on. The second key feature of an SSD is its internal parallelism. The NAND chips can be reached in parallel over multiple channels. This internal parallelism allows the FTL to handle concurrently both internal operations as well as user requests. This concurrency and how it is able to use the available parallelism is the source of the variability. FTLs, unfortunately, are a closely guarded trade secret, and we do not have access to them in order to find the precise cause. So what we do in this paper is we look at performance variability from a user or application perspective. And what we do is we analyze the symptoms and then we look at possible mitigation strategies. Now, what user level mitigation strategies am I referring to? Well, the question we ask in the paper is whether we can mitigate the variability by more aggressively exploiting internal SSD parallelism. And this is possible at the user level in the following way. As you can see in the figure, the device driver in the hosts send I/O requests to the SSDs. And these requests are relatively small. They're hundreds of kilobytes to megabytes in size. To be more aggressive, one can instruct the device driver to send more concurrent requests as well as larger I/O requests. And the way we do this is by either using direct I/O or a tweaked version of buffered I/O, as I will be describing later. Before I dive into the analysis, though, I have two slides on methodology. Our SSDs are accessed using the following access pattern. single-threaded reads of relatively large size, 256 megabyte. The accesses are sequential and using buffered synchronous I/O with the default configuration. We chose this access pattern because it's popular, it's employed by many applications, and also it is simple enough that it makes the performance variability stand out. More complex access patterns are possible, but they could hide the variability. And we use HDFS. HDFS generates this access pattern that I just described, but we also corroborated the results by using the FIO tool, and the results match. In this talk, I will only show HDFS though. In our experiments, we have HDFS repeatedly read the same 256 megabyte block. We made sure to remove all other sources of interference with the SSD. For example, other processes or file system journaling or so on. And we use ext4 as a file system because of its popularity. As hardware, we have 3 different SSDs, which I will call A, B, and C in the presentation, but you can find all the details in the paper. It's important to note that our SSDs have had low lifetime usage, and also the disk capacity utilized during the experiments was also low, under 20%. As a metric, we measure read throughput at the HDFS level, and for analysis, we also looked at I/O request latency. The slide here is just a high-level depiction of the performance anomalies. There are 2 main takeaways here. First, each of the anomalies results in a 10-15% read throughput drop individually. Second, each of these anomalies happen at different time scale. And the names are the names we have given to each anomalies. So intrinsic slowdown occurs at the granularity of seconds, temporal slowdown at the granularity of minutes, hours, and permanent slowdown at time granularity of days. Now let's start with intrinsic slowdown. What is it and how does it manifest itself? Well, assume that this horizontal line shows in order the bytes in an HDFS block as it's being read. The block is spread over 3 different file system extents. To read the data, the host will send a number of I/O requests to the SSDs. Now these blue rectangles are I/O requests, and I am showing here just a small subset of them for illustration purposes. Intrinsic slowdown refers to the fact that a number of I/O requests at the start of each of the file system extents are read slower than the rest of the I/O requests in an extent. If we were to depict read throughput at the very high level, it would look like this. Lower for the affected I/O requests, the ones encircled in red, and larger read throughput for the rest. Again, to emphasize, intrinsic slowdown affects the initial I/O requests in each ext4 extent, and the duration of the anomaly is variable for each extent. In some cases it lasts 10 requests, while in others it lasts 200. And it results in a 10 to 15% read throughput drop. We analyze the problem further, and we first look at I/O request latency. The plot here shows a CDF of request latency for the 3 different SSDs. The x-axis shows request latency for individual I/O requests in one HDFS block, while the y-axis shows percentiles. Dotted lines are for the I/O requests unaffected by the intrinsic slowdown, while solid lines are during the affected periods. And notice that the latency is increased at all the percentiles. At the median, we see 25% increase in latency. Intrinsic slowdown impacts all three SSDs, but it is worse on SSDs B and C. We also looked at whether the extent size is a factor, but we found no correlation. The second performance anomaly is what we call temporal slowdown. This is again a plot with time on the x-axis and read throughput on the y-axis. Encircled in red are the three instances of temporal slowdown. As you can see, they are sudden and reversible read throughput drops. These drops are periodic. On SSD A, they occur roughly every 130 minutes. And they are temporary. On SSD A, they last about 5 minutes. This anomaly results also in a 10–15% read throughput drop. To analyze further, we look again at I/O request latency. This time, we see that the latency increases mostly at the tail. We see a 78 increase in latency at the tail. The problem appears both on SSDs A and B, but I am focusing just on SSD A in the talk. You can read about SSD B in the paper. The key point here is that there are no writes in the system. And we verified this. So while this anomaly may look like garbage collection, it is not. It appears even in the complete absence of writes. We further asked whether this periodicity is correlated with the read activity or it is simply time-based. And we found no correlation with the read activity, but rather we found that the temporal slowdown occurs as if it's triggered by a timer. The third and last performance anomaly is what we call permanent slowdown. This is the initial plot you saw in the talk. Time is on the x-axis, read throughput on the y-axis. At a moment in time, read throughput drops and never recovers. It takes days, sometimes more than 1 week, for this problem to appear. And as you can see in the plot, it takes about 1 hour to fully set in. But once it does set in, it is irreversible. This anomaly also results in 10–15% read throughput drop. Looking again at CDF of I/O request latency, we see latency increasing at all percentiles. At the median, there is a 25% increase. This only appears on SSD A. The key point we found is that there isn't a single drive-wide event causing this. This occurs on a per-file basis. At one moment in time, a file may become affected, while the others remain unaffected for the moment. This is again the high-level slide listing all the anomalies. I want to emphasize also here 1–2 key points for each of them that you can remember. So intrinsic slowdown affects the start of an ext4 extent. Temporal slowdown occurs periodically even if no writes are present in the system. Permanent slowdown is irreversible and happens at the file level. Now, each of these anomalies results in a read throughput drop of 10–15% individually, but these anomalies can in some cases all appear simultaneously. And in that case, there is an aggregate read throughput drop of up to 30%. So can we mitigate these slowdowns? More precisely, the question we ask is, can we mitigate them by aggressively exploiting internal SSD parallelism? So how can we be more aggressive at the user level? Well, we can do that by sending more concurrent I/O requests to the SSD and by making these requests larger. The table here shows the different settings. On the left is the one labeled default, and this is the standard one which presented all the vulnerabilities, all the variabilities. The last two columns are the more aggressive approaches. Notice how the request size and the concurrency are both increased. And we find that being more aggressive in exploiting internal parallelism does help, but it is not a complete solution. This mitigates intrinsic and permanent slowdown, but actually not the temporal slowdown. This is a brief slide discussing the meaning of the findings. We've seen that the default access mode to the SSD is sufficient in the common case, but it is suboptimal during periods of slowdown. We have also seen that being more aggressive in how I/O requests are sent can help mitigate slowdowns. So I want to leave you with a question: can we build more adaptable storage stacks that can automatically detect slowdowns caused by hardware and adapt by temporarily becoming more aggressive? There is plenty of related work, more than I can describe in this talk, but I want to focus briefly on a few categories of related work. First, there are several papers that describe slowdowns caused by internal operations that need to perform error handling. Internal operations like this may have to correct read retention or read disturbance error, or they may need to reconstruct data. However, in related work, this behavior is highly correlated with high SSD lifetime utilization. So these happen more on worn out SSDs. The difference is that we show similar problems can occur even in SSDs that have low lifetime utilization. Furthermore, slowdowns have been shown to occur also because of aging file systems, and this typically involves lots of prior activity in the file system and many small files. The difference is that in our case, we show that similar problems can occur despite having a fresh file system as well as large files. Finally, there are also studies from the wild which corroborate our findings. In a FAST 2016 study, the authors find that SSDs may present hour-long drive-wide slowdowns. In conclusion, in this talk I introduced 3 new types of performance anomalies that result in significant read throughput loss. They happen at different time granularities and can lead to 10–15% read throughput loss individually and up to 30% when they happen concurrently. And I've also shown that partial mitigation is possible by more aggressively exploiting internal parallelism. I want to thank you very much for listening to my talk, and I encourage you to read the paper for the full set of details. Thank you.